Hey everyone, Mr. Moidian here with our snow day lesson. Go ahead and take a look at this warm-up. I encourage you to pause the video, try it out on your own, and then click unpause to reveal the solution. I guess Maui has her opinion on the problem. If you hear a meow, it is my cat. She's nearby and she's curious about the computer situation here. All right, let's take a look at this problem. Hopefully it looks familiar to what we saw last week before the snow. You can rewrite this problem thusly to make it look a little more familiar to the ones we've been seeing with the reverse chain rule. And the question to ask is the inside part, so to speak, in this case it's the underneath part, is one of them the derivative of the other? Well, it appears that if this is the fourth power, then the third power would be its derivative, except for a coefficient change, right? So what we want is the derivative of this part to be attached or chained onto it. So is that what we have? We want the derivative of the bottom here, which is negative 16x to the third. We want that to be next to it. It's not, right? Because the coefficient is wrong. However, we can tweak this coefficient, and only the coefficient, in order for us to have negative 16x to the third. So we do that by multiplying effectively by 1, but a very tricky or useful form of 1. So we have this number added, multiplied to the problem, or added additional to the problem, and then it's reciprocal as well. Therefore, we have negative 16x to the third, because the net result of this operation is to create what we want. And moreover, the net result of these two operations here and here is cancellation, right? So we're safe. So now just to double check, do we have the derivative sitting next to it? Yes, we do, right? So all smiles. So now we can effectively ignore this portion of the problem. And this is where sometimes people get a little confused. So let me try to illustrate it the best I can. We can effectively ignore this portion, right? We know its origin. It came from the part that we've underlined here. So rolling back the clock, what we effectively have is 1 over this business here. So now we have to remember, well, what is the antiderivative of 1 over something, 1 over x in general? Well, that would be ln of x. Now keep in mind, we have to put these absolute value bars here because the original function, both this one here and this simplified version, have as its domain any number except that which makes the bottom equal to 0. So negatives are fine, right? But that's not the case for ln. The ln operator cannot accept a negative result. So to avoid that, we simply take the absolute value of whatever we're taking the natural log of, and therefore we avoid that problem. So 1 over this crap is going to be ln of that very crap, absolute value, so that's what I have here in blue, plus c, of course. And then we're going to multiply by the same coefficient that was there that made this possible, right? This little adjustment, if you think of this as sort of like a tweak or a fix, this is what makes the math relatively straightforward. 1 over x, ln of x. So 1 over this is ln of that. So go ahead and multiply through by the negative 3/16, and the first part's going to be exactly as you expect, right? Now keep in mind, plus c is just a placeholder for a constant, so negative 3/16 of some unknown constant is just going to be some other unknown constant, so we just call it another plus c. Keep in mind, these plus c's are different, but they're just placeholders, so it doesn't really matter what's one or the other. So this problem made sense, then great. If not, then the next portion may help you figure out better as to what's going on. If we take a look at the reverse chain rule in abstract form, it looks very much like the normal chain rule, except in reverse, hence the name, right? The original chain rule that we learned back in October or so had this portion first. The derivative of a composite function was what we have here as the integrand, right? So by design, what we're looking for is the part that is living inside another function, right? Is that part's derivative chained on? If so, all smiles, right? But if not, if it differs only by a coefficient, we can tweak it as we did in the previous problem in order for this happy result to occur, right? And if that happy result is what we have, then just like before, we can ignore the chain once we've allowed it to come into existence. F prime's antiderivative is just f, right? And the argument is still g of x. It's still the part of the function on the inside remains on the inside. So with that in mind, let's take a look at this problem right here. Now you might be thinking, right, looking at this, looking at this. However, if you go ahead and rewrite tangent as sine over cosine, this problem becomes much more approachable. So I encourage you to pause the video this time, try this one out, look back at the warm-up because they're very similar in many regards, and see if you can arrive at a possible answer. So looking again, we have the sign, which you can write off to the side here as this. What we want, right, is the derivative of the inside, or in this case the bottom part, to be attached to it. So we want cosine's derivative, which is negative sign. Well, this is just positive sign. However, that's a very easy fix, right? Just throw a negative right here, as well as right there. Because these two blue negatives, of course, make the net result of positive. So all's good there. So continuing onward, we now have, whoops, over here, we now have what we want, and I went ahead and marked it out just to illustrate. Now that this is negative sine x, that's in the red, or behind the red there, we can effectively ignore it, allowing us to focus on 1 over stuff. And just like before, 1 over stuff's antiderivative is ln of the absolute value of that very same stuff. Of course, keep track of this negative out here. It's going to be very important in just a moment. Go ahead and distribute the negative. Keeping in mind plus c times negative 1 is still plus c, because it's not necessarily minus c, because if c was negative to begin with, then of course it becomes positive. So it's just a placeholder, so plus c. Now, if you did try this one, I would pat you on the back, metaphorically, if you were able to get to this magenta step. Because for the most part, that's effectively like the warm-up, and it's an answer. It's not necessarily the answer. It's acceptable, but not perfect. And I'll tell you why. Unlike the previous problem, this coefficient here of negative 1 has some interesting properties that we can apply. Now, it's true that the 3/16 we had earlier can also be applied in this way, but negative 1 is a little more useful. Think back to logarithm properties, and the most important one I want you to draw your attention to is over here. A coefficient times a logarithm can, and this works in both directions, can be thought of as being an exponent. Remember, logarithms are exponents, so when you exponentiate something you're taking logarithm of, it's the equivalent of multiplication. I'm simplifying that a little bit, probably too much. In any case, this log property hopefully looks familiar to you, which is to say, you can take this negative out here and put it up top, right? So to go from magenta to orange, all I did was apply this property with this negative 1 out here. Well, cosine to the negative 1 power is hopefully ringing a bell. It's not inverse cosine. Remember that negative 1's a little misleading. It's not arc cosine, but rather 1 over cosine, better known as secant. So the real answer, or in a sense, is this green answer right here. So if you follow the logic, you see that a lot of it's very similar up to the magenta. And then just going one step further using this property, you get to the green. So this result can be derived on its own. If I ask you what's the integral of tan, sure, you can rederive this result by just solving this exact same problem, but it is a useful formula to know, right? So on the next slide, I have some formulas for you to write down. Some of them we've already seen already. We just haven't added them to our booklets, and this one is going to be one of our new ones. So we've already seen this one in class, and also some more just now. This one's pretty straightforward, and this one is sort of its cousin. Remember, A is just a number, that's not E, although it could be E. This is just a generalization of this rule right here. So those are fairly straightforward, just the opposites of the derivative rules. However, these are the new ones, or particularly new ones. The one we just showed, right, tan becomes ln of absolute value of secant. By the same token, right, so we're not going to actually prove this, but you can imagine how one might. Cotangent antiderivative is ln of sine, absolute value. So the exact same argument except for a couple of different substitutions. These two are a little complicated, but we're not going to prove them again. The way you find both of these is literally to emulate the argument we just did for tangent. So this process can be used to derive other things, or antiderive, I suppose, and we simply use that process to define these results. So as long as you have these results and can apply them, as we will in some future homeworks, you'll be good to go. Okay, so add those when you get a chance, either now or later. Let's take a look at a few more. All right, integral of, or antiderivative of, cosine of t times sine squared of t. Now notice this is dt now, right? Not dx, but as long as these match the variable and the variable of integration, you're good to go. So try this one out, pause it, play around with it, ponder, and see if you can figure out the answer. And let's take a look. It'd be a little more illustrative to rewrite this as this stuff squared, And then the question to ask is sine, which is the inside part's derivative, sitting next to it? Well, for once, we're all smiles ready to go. There's no adjustment necessary, right? Sine's derivative is cosine, and what we want is what we have. No adjustment needed. So once again, we can ignore this business. This crap to squared, if you take the antiderivative, is going to be that crap to the third power divided by 3, right? That's just the reverse power rule. And that's it. Don't believe me? Take the derivative of this blue answer, and you will get the original problem. So this is a sort of, I don't want to say a simple version of the reverse chain rule, but one that allows you to see the moving parts a little more directly. When there's no tweak, it's a little more straightforward, right? But keep in mind, being able to adjust problems to your liking is what makes math powerful, right? Taking something unfamiliar, adjusting it to make it fit your new perspective. We have 2 more to look at. So on its surface, this one looks kind of scary, but try it out and then pick it up from here. So I imagine many of you probably weren't sure where to go. Maybe not, we'll see. And one way to go is to rewrite the terms thusly. So get each part with the x in there ready for calculus, right? So that's ready for prom, and so is this. Now it's a natural question, well, which one is the original and which one's the chain, right? Again, a pattern you may have noticed is the chain is typically out front, although not always. And moreover, the exponent here is 1 less than that one. So the question to ask is the derivative of this portion here chained onto it? Well, the derivative of that portion is negative x to the negative 2, and that is almost what we have, but for this pesky 2 right here, right? So we need to turn this 2 into a negative 1, right? Because that's the number that we want to be there. So we do that by multiplying by negative 1/2. The cost of that, of course, is to multiply simultaneously by a negative 2. So these two have a net result of nothing, right, times 1. Now we have what we want, so all smiles. The 2 negative 2 out here made it possible. So once again, we can ignore this portion. Its origin has been identified. We can now figure out the ancestry of this part. Where did this come from? Well, mercifully, the integral of e to the x, or e to the something, is still e to the something, just like the derivative goes in the same direction. So e to that is e to that plus c. Go ahead and multiply by negative 2, and you'll get the answer there. Now, notice the original problem had no negative exponents, so always be kind and rewind, turn it back to the original form. So this would be 1 over x, and everything else stays as is. Oops. There we go. One more to look at, I believe. Indeed. So this one looks pretty intimidating. Get some trig, you got some exponents, you got some radicals, quite a bit of business occurring there. So think about it, see how far you can get, and then unclick for the answer, or I guess click for the answer. So let's take a look. Hopefully you recognize the radical sign is getting in the way, so let's rectify that by writing it to the 1/2 power. And the part you may not have recognized, although it's not really needed, although I will say it makes it easier, notice how this 4 and this 4 match, and that's pretty good, right? This 3 is sort of throwing a wrench in the works. So I'm going to just factor it out. I'm going to move it out here. And that'll allow me to just focus on the portion inside the integrand, to use the correct vocabulary, right? So I don't really have to worry too much about the 3 and have to worry about fractions too much, although I will have some fractions. In any case, the inside portion here, tan of 4x, what we want is its derivative sitting next to it. Well, what is the derivative of tan 4x? The derivative, mind you. Well, that would be secant squared 4x times 4 with the chain rule, the straightforward original chain rule, right? So this 4 came from this 4x chained on. That is not what I have here next to it. However, I can simply adjust the blue secant squared 4x by attaching a 4, which is what I want. Of course, the penalty for that 4 is to multiply by 1/4, right? I'm planting the evidence, so to speak, to mix metaphors. But the net result of these two greens is to not change the problem at all. Of course, the 3 is out here to begin with, so this 3 and this 1/4, of course, will multiply to give you a new result, which we'll see in the next slide. So I couldn't fit all this on one slide, so hopefully you have this step here, keeping in mind what's going to happen on the outside. 3 times 1/4 is, of course, 3/4. So it didn't change anything else except for that leading coefficient. Do I now have the derivative of the inside sitting next to it? Indeed I do. So that allows us to once again ignore this portion of the problem. It's going to just pop back inside like little Russian dolls. So stuff tan to the 4x raised to the 1/2 power is just going to be the reverse power rule. So go up by 1. So it's going to become 3/2. Again, the same argument there, tan to the 4x, so 3/2. Of course, divided by the same number, 3/2, right? This is like that sine cubed problem from a moment ago. In a way, this red answer is the answer. It's just not a good form of it. So let's correct that a bit. I'm going to take out this divided by 3/2. To divide by a fraction is equivalent to multiplying by its reciprocal. So that's where I got this purple result. The only change was this red denominator came out front here. I'm going to go ahead and distribute the 3/4 here. So 3 times 2 will be 6. 4 times 3 is 12. And then 3/4 of c is just some other c, so who cares? So I get that result there in green. 6/12, of course, is 1/2. Once again, the original problem, which is no longer on the slide, had a radical in it, no fractional exponents. So turning this back into a radical, the over 2 signifies a square root, and the cube on top tells us we're cubing the radicand, so that's going to be this result right there. And if you take the derivative of this thing very carefully, you will eventually get what we started with. All right, so stay warm, and I'll see you on Friday.